Welcome to the Future of Structures podcast, where we talk to the experts who are evolving our buildings for tomorrow. And here is your host, Adam Jones.
I just had an interview with Professor John Provis, who is a professor at the University of Sheffield as a chair in cement materials science and engineering. So he completed his degree in chemical engineering in 2002, and since then has been passionately following research in cement. So John was awarded the 2013 William Robert Hermit Medal in recognition of his outstanding contribution to the research and development of geopolymers and other construction materials. He was also awarded an honorary doctorate by Hasselt University, Belgium in 2015 to recognise his leadership in geopolymers and other cementitious materials. And he also has funding for European Research Council, as well as UK research councils and industry and so on. So it was an absolute privilege speaking to John. He's one of the most educated people on the planet in cement and supplementary cementitious materials. So it was a conversation rich with details and technical know-how about cement. So I hope you guys learn as much as I did and enjoy it as much as I did. Without any further ado, here is John Provis.
All right, so as an undergraduate, I studied chemical engineering and mathematics at the University of Melbourne. I got into research almost by accident because my summer job fell through. So I was offered a research position over the summer and working for a professor who I found I got on very well with. And off the back of that, he offered me a PhD and said, oh, by the way, it's on cement. And as a chemical engineer, my response was, hang on, I don't know anything about cement.
Yep.
And it turned out that was actually an ideal starting point. Because the work we do, or the work I did in my PhD and then where I've moved on to since then, has been, let's say, non-conventional cements. Yep. So not just traditional Portland cement, but looking at alternative ways of producing materials of comparable performance, but with greatly reduced CO2 footprint and or greatly improved technical properties by coming at it from very different angles. So awesome. I did my PhD in Melbourne as well, then worked there and led a research group there for 5 or 6 years. And then I was offered a job as Professor of Cement Materials at the University of Sheffield in the UK. So I've now been here for 5.5 years.
Yeah. Awesome. So just before we started this interview, we were starting to talk about how you recently went to a sustainability conference in Cuba where they were discussing how to cater for the supply or the sheer supply of cement that is going to be going through Cuba and some other developing countries. So can you tell us a little bit about what this was all about and what you were speaking about in Cuba?
So the focus of the conference was calcined clays in cements and concretes. So in Cuba and some other countries as well, there's rapid growth in the demand for cement. China alone used as much cement in the past 2 years as the US did in the whole of the 20th century.
Wow.
The growth is just phenomenal. And the ability to construct new cement production facilities, the kilns, the high temperature process that makes the Portland cement clinker, that is in a lot of cases a limiting factor.
Okay.
So we're looking more and more at blending cements with high percentages of what we would call supplementary materials, supplementary cementitious materials.
Yep.
And the calcined clays that we were discussing in Cuba are a local option that is ideal for them there because they've got very good clay resources, actually very good limestone resources as well. So they blend limestone, calcined clay, and quite a low percentage, around about 40 or 50% of Portland cement to make a concrete with very, very good performance. Places like China, the average replacement level of the Portland cement in their concretes is more than 40%, heading towards 45% replacement by, in that case, mostly industrial byproducts.
Yep.
So as this growth is happening worldwide, just to meet the demand for the materials, we have to go to what are, I would say almost by accident, a much more sustainable solution anyway.
Gotcha.
Because the CO2 footprint of these supplementary materials is much lower than the CO2 footprint of cement. Just to meet demand, we need a more sustainable material. And almost as a happy coincidence, it's far more sustainable.
Yep. Awesome. So with that, so you say that creating the kilns for Portland cement's a really tough process. So these kilns, it won't be able to supply the demand in the future. So then when we need supplementary cementitious materials, and what about the can you talk about a little bit the binding product as well that might go in with the supplementary cementitious materials?
Well, I think the kilns themselves, honestly, in most countries are not the limitation.
Yep.
It's only where there's very rapid growth, and the issue with installing the kilns is the capital cost. A kiln can cost $500 million, pounds, or euros.
Yep.
So to get that investment on a quick startup time, where you're working in a developing environment and growth is fast but capital is not enormous, that can be one of the limitations.
Gotcha.
The binding products, as we're looking at, Portland cement reacts with water and basically is the glue that holds together the concrete.
Yep.
It makes a calcium silicate hydrate binding phase, which ties everything together. Now, you can make calcium silicate hydrate of a very similar nature by reacting, well, let's say Portland cement or similar materials with just about anything else that's got a lot of silica in it that's reactive.
Yep.
So the most important ones that are used worldwide at the moment are blast furnace slag, which is a secondary product from iron manufacturing.
Yep.
Or coal ash or fly ash from coal-fired power stations. Or, as I was saying, calcined clays or some natural zeolites, natural mineral resources that you can dig up and use more or less directly in where the geology suits.
And say the developing countries, they don't have the big cement kilns there already, are they more suited to using geopolymers as well for the same kind of reasons they're more suited to using supplementary cementitious materials?
They may well be, yes. The complication in making a geopolymer type cement or any other, say, chemically activated cement is that you need to supply the chemical activator instead. So you always need some form of chemical process, whether it's a cement kiln or whether it's producing a chemical activator to make a geopolymer.
Yep.
The advantage of using a geopolymer type cement, which are, let's say, you'd use 90 or 95% the materials that I just described as being these supplementary cementitious materials,
yep,
mixed with a much lower volume of a highly reactive chemical activator. If you're transporting materials, it's much easier to transport something which is 10% of the quantity of cement rather than 60 or 70 or 80% if you're shipping in Portland cement from somewhere else.
Gotcha. Yeah, cool. And so if they were to use fly ash and blast furnace slag, and I know in the building industry there's a lot of people a little bit hesitant because it affects the build times, people think. So is there any way, does it have to affect the build time every time you replace cement with fly ash and slag and other materials like that?
Not necessarily, no. In European construction practice, it is almost unheard of at the moment. It would be around about 20 or 25% of the cements that are sold in Europe are not blended with anything so when they're produced as a cement. And those ones that aren't blended with anything as they're produced would then normally be blended with one of these supplementary materials at the point of mixing it into concrete. So the production of non-blended cements in Europe has almost almost died out.
Okay.
Because the cements themselves, I think the strength at 7 days or at 28 days is massively higher than what we were achieving 20 or 30 years ago. And the use of admixtures and additives to control flow characteristics, to control strength development, this has come ahead in leaps and bounds. So I would go so far as to say what we can do with modern cements is near enough to magic. And the blast furnace slag and the fly ash actually really help with some of that. Because the Portland cement component in these blended cements is giving very good early performance. And in the European strength gradings for the concretes, and I know Australian standards don't have the same structure and charts of strength development as the UK one, or as the European ones do.
Yep.
But the requirements for strength development for a 52.5 megapascal grade cement are exactly the same, whether it's a plain Portland or whether it's blended. And the blended cements that are sold to that grading meet the requirements of that grading.
Yep. Yeah, nice. So when you're doing your research on cement, what are some of the other properties that you are working on, say things like durability or shrinkage, and how are these other properties affected with replacing it with supplementary cementitious materials?
The durability characteristics are in most cases massively improved.
Yeah, wow.
Because as we're designing a concrete for a specific 28-day strength, specific performance of 28 days, if we've made that concrete using a blended cement, the intrinsic strength development and properties development of that cement will go on for a lot longer. So basically, at 28 days, a plain Portland cement has given you most of what it's got to give. It's finished.
Yeah.
The supplementary materials, the blast furnace slag, the fly ash, the calcined clays, these continue reacting for a lot longer. So you'll have near enough to equivalent performance at 28 or 56 days, because that's what the standards tell you have to achieve, and then continuing improvement in that performance over time. So just as a concrete example of this, my father, who lives in the suburbs of Melbourne, was digging out an old septic tank from behind their house.
Yep.
And most of the concrete was sort of a medium grey colour, and he could chip that apart with a crowbar. And there were some bits that were a slightly darker grey that he couldn't break. He had all sorts of sledgehammers and things like that, could not break this slightly darker grey concrete. He brought to me, knowing that I'm interested in such things, brought to me a piece of the normal one and a piece of the darker grey one. And this had been underground, serving as a septic tank for maybe 35 or 40 years. And the regular concrete was perfectly good regular concrete. It was doing what it should have done.
Yep.
The slightly darker grey one, it was pretty easy to identify was a fly ash concrete. And so when that was put into place, that would have been a very similar characteristics to the rest of the stuff. But 35 or 40 years down the track, he couldn't break it in the same way. It was tougher, it was stronger, it was harder.
Cool.
In terms of things like chloride transport, so in a reinforced concrete, you have to keep the chloride outside to stop steel rusting. If you're in a marine condition, or in a cold climate, if you have salt on the roads as well. The chloride is what limits the service life. And in these challenging conditions, the vast majority of concretes that are specified for marine exposure in Europe are high volume blends of supplementary materials with maybe 30, 40, 50, 60% Portland cement in them, because that's how you get the durability you need. And as I said, as a happy coincidence, they're also more sustainable.
Yeah, nice. Yeah, I didn't realise that. So Sounds like anything in that kind of environment, or do you think infrastructure projects, I know they're building the Melbourne Metro at the moment, and they'll be going underground and reacting with materials underground and water and things like that. So a higher percentage, is it better for infrastructure projects like that as well?
In almost all cases, yes. I would say if you can get a reliable, high volume, inexpensive supply of these supplementary materials, then they will always give you better performance in a long-term durability application, with the possible exception of if you're under severe carbonation attack. So CO2 from the ambient atmosphere coming in and attacking the concrete, if that is the main limiting factor in the service life prediction of your concrete, the performance of a high volume blended cement will be similar or maybe not quite as good. But conditions where carbonation actually limits the service life of concrete, as opposed to conditions where carbonation is predicted to but then turns out not to, which is far more common. Yep. But yeah, conditions where it's limited by carbonation are quite rare in most parts of the world. Middle Eastern climates being a partial counterexample to that.
Okay, gotcha. So in developed countries, if we're trying to specify high blend of cement, is the supply chains that are already here supplying Portland cement, is that a big hurdle for us because we've already got the systems in place to be able to supply massive amounts of Portland cement, which is probably cheaper for us at the moment?
I wouldn't necessarily have said so. And particularly in the Australian context, and Australia produces about as much fly ash as cement anyway.
Yep.
And a cement company is expert in making cement. That's absolutely for true and for certain. However, the thing that cement companies are probably better at than most other organizations in the world is the logistics of bulk powder handling. And fly ash or blast furnace slag, these are bulk powders. So if you know how to handle cement, you know how to handle fly ash or slag. And handling them, shipping them, getting them where they need to be in the right quantities and at the right time is absolutely critical. So for any player in the industry, the opportunity, and I would say it as an opportunity, is by using these materials, by using sustainable materials, there's a resource there, which means you can make excellent quality, sustainable concretes, whether they be geopolymer concretes, which are made almost entirely from these supplementary materials, or whether they be high volume blended concretes. The opportunity is to grow production while shrinking CO2 footprint using existing supply chains or expanding upon existing supply chains.
Awesome. So is this a trend you're seeing, this push towards kind of green concrete? Now you've been researching it for a while. Is industry kind of pushing this way as well? Absolutely.
Yeah. One of the initiatives that's going on in Europe at the moment is it's an industry-funded research organisation called NanoCem, which is focused on the nanoscience of construction materials, particularly cement, but with a view towards achieving better technical properties and sustainability. So this is a research initiative involving, I think, 7 or 8 industrial partners and about 20 university or government labs from across Europe. It's been running for 12 years now and made enormous leaps forward in understanding how cements work at the nanoscale. But that really deep fundamental science is funded by the cement industry, who want to, essentially they want to make more money by making cement. but they've recognized that the way they can do that sustainably in an economic sense is to do it sustainably in an environmental sense.
Gotcha.
Because if you are seen to be doing things that are unsustainable, you will be stopped from doing them.
Yeah, definitely. So when you're looking at sorry, John, when you're looking at the nano kind of scale, what kind of changes can be made when it's such a small scale with the particles and all of that?
Surprisingly many. And I would say the best example of this is the use of superplasticizers. So superplasticizers are small polymer compounds. So it's a liquid or a powder form that you add this in at maybe 400 or 500 grams into a ton of cement. And so this is very low doses. And as you're blending, you combine this with the cement and make concrete out of it, or you can mix it directly in at the concrete scale. But as you're combining the superplasticizer, it sticks on the surfaces of the cement particles. So the polymer molecules, the polymer chains stick on the surfaces and control how the particles interact with each other. The difference you can get in the flow of a concrete by having included a superplasticizer is keeping every other parameter of the mixture the same. You can turn something that basically, so if you fill up a tin can with it, invert the can on your desk and lift up the can, it would, starting from a concrete that would more or less maintain its shape when you do that. It's a test we call the slump test. It's a very simple one. Essentially a cylindrical mold or a cone-shaped mold of concrete. Lift up the mold, how far does it sag? And so you can go from something that is almost a zero slump, almost holding its shape in that test, to something that flows basically like cake batter.
Nice.
And
is that for high strength concretes as well?
It's for all sorts of things, particularly for flowable, pumpable concretes. So I'd use the example of the Burj Khalifa tower in the Middle East, where they're pumping concrete up 70 or 80 floors. And if you think about fresh concrete as a material which has a fluid component and rocks floating in it, and those rocks, I say rocks floating because they have to stay equally distributed throughout the material. And if you were to, say 30 years ago, to make a concrete flow better, you'd put more water into it, which ruins the durability properties, ruins the strength properties, but makes it more flowable. Unfortunately, when you do that and then try to pump it, and pumping it vertically, if you can imagine taking a bowl of cereal full of milk, tipping that upside down on your desk, the cereal stays where it is, the milk goes everywhere.
Yeah, nice.
Your concrete would do the same thing. It segregates, it splits. So you've got a car park full of rocks down the bottom, and only the cement paste gets to the top. So the superplasticizers can reduce the water content of the concrete while keeping the same flow characteristics, or improve the flow characteristics, but also stop it segregating. And if you can just imagine what it would take in terms of chemistry, in terms of controlling the properties of the fluid component of the concrete so that it's pumpable. You can pump it up hundreds of meters into the sky without these rocks that are much more dense than the rest of the concrete separating and falling down. The nanoscale control of the chemistry at all of the particle surfaces is what enables that to happen. That's done by basically molecular level tweaking of the properties of the properties of the cement, and using these organic molecules, the superplasticizers. As a spin-off from this, by reducing the water content, and a good superplasticizer will reduce the water content of a concrete to keep the same flow characteristics as without the super plasticizer, you can use 15% less water, a lot of them 20% less. Now, reducing your water content by 15 to 20% can increase your service life enormously. Your durability characteristics go through the roof.
Yeah.
So this type of approach to improving the performance of concrete by molecular level engineering of the clever things we like to add to it, this has been an enormous jump in how we understand and use cement and concrete. I would say that cement is probably the most chemically complex, non-biological chemical reaction system that we study. It's more complicated, there's more different things going on than just about any other process. A reinforced concrete you could describe as a composite of 14 distinct identifiable phases. Most composite materials have 2 or 3 phases. We're looking at a composite of 14 phases.
And by phases, you mean, can you elaborate on phases?
Right. Identifiable minerals so you've got air bubbles, water, steel. The cement, the unreacted cement has 5 different minerals in it. The reaction of the cement produces another 4 or 5 different identifiable minerals, all in particles that pack together to make this binder that sticks everything in place. And then you've got aggregates as well. So every length scale from, centimeters down to nanometers. So what's that? 1,000th of the width of a human hair. You have interesting and complicated structural features to understand and manipulate. This is why I enjoy my job.
Yeah. No, I'm personally much more interested in cement after this conversation. So, and with the research, is it like it's going to hit some kind of roof where cement technology or the research you're doing can't get any better, or is there a lot more innovation on the horizon? And if there is, then what does this look like?
And I currently have more than 30 years until my scheduled retirement date. I have absolutely no fear that I'm going to run out of things to do in that time.
Awesome.
The best experts in the world get together on a very regular basis to sit down and argue about exactly how and why cement goes hard. There are fundamental details of that setting and hardening mechanism and of the fundamental nature of the chemical phases, the products that are formed. So much of this we don't understand at all well. And despite this, we can manipulate it, we can control it, because we know all sorts of ways to control what's going on using the knowledge we have. That's not to say we have enough knowledge. As an academic, I'll tell you we never have enough knowledge.
Yep.
I'd be doing myself out of a job if I said anything else. But there are so many opportunities. Every time we think we know everything, another opportunity pops up. Opportunity is often disguised as a problem. So we've talked a lot about fly ash. In the UK, in the next 5 years, coal-fired power generation will stop. So we won't have fly ash available. And this is a real problem for a lot of civil and infrastructure engineering work, where they rely on fly ash concrete to do very large volume pours, for example, foundations, because blending fly ash with cement means that the heat release as the cement is reacting is more moderated. So the foundation doesn't overheat as the concrete's hardening. If you don't have fly ash available, you need to find another way to control this heat release from your concrete as the concrete's reacting.
Nice.
So changes in society, changes in the structures of other industries, changes in how we use cements, changes in what we need from them, durability demands. Now we're designing infrastructure with a 200-year specified service life. 50 years ago, they wouldn't have dreamed of that. So everything that we're doing is focused on a more sustainable, better future for infrastructure. But sustainable is not just CO2 footprint. Sustainable is in the context of everything that happens in society. And coming back to the calcined clays discussion and the meeting that was held in Cuba, one of the reasons for the interest in calcined clays is that there is so much clay in the world that can be inexpensively processed to make a desirable supplementary cementitious material, even in places where fly ash availability or slag availability may become a restriction on using those materials instead. I mean, worldwide, these are an enormous waste disposal problem, particularly fly ash. And the Tennessee Valley Authority had a big spill almost a decade ago now and contaminated a large area down a river with fly ash that burst out of a dam. It was considered a hazardous waste disposal problem.
Wow, yep.
But if you take all of the fly ash in the world, there's probably only enough to replace maybe 15% of the cement in blends.
And is that including the fly ash in the ground? I understand some countries might have stored it from, decades and decades ago. Is that including that supply?
The 15% is what's currently being generated. As coal-fired power generation ramps down in a lot of countries, these stored resources, the stockpiles of fly ash, will become much more valuable. At the moment, there are a few steps towards extracting fly ash from these mines or these stockpiles. I've seen some interesting work being done in the US on that extraction as well. The part of the problem with getting it out of those stockpiles is that what you really want from fly ash is a dry powder, and when it's stored wet. And also you need to do a lot more quality control work on understanding what was done in the past to figure out what actual ashes you've got. How contaminated are they with all sorts of other things? So that is it's an attractive possibility for the future going forward. Whether that turns out to be I would be surprised if it replaces the use of freshly generated ash, if there is freshly generated ash available in sufficient quantities.
Yep.
Where there isn't, it can fill that gap.
Awesome. And do you see your work intersecting with other technologies that are coming on the horizon, like robotics and 3D printed buildings and all of this kind of stuff? How does the concrete you're researching go with these new technologies?
The 3D printed concrete buildings, I would say, are an interesting way to generate high-value architectural products.
Yep.
Or potentially to enhance throughput in the precasting area. I wouldn't see bulk production of 3D printed units ever becoming cheaper, easier, or faster than a simple casting process where you don't have a complex geometry. So if you're making blocks or panels or something like that, it's easier to just pour your concrete out of a mixer into a mold and have it harden there. Where 3D printing really comes into its own is for specialty things, so architecturally beautiful products. 3D printing a house on site has been done. My personal opinion is that that's a difficult way to go. I don't think that's going to be a cost-saving measure.
Yep.
But it's a really neat demonstration. And it shows what the technology can do. But I think the best use of that technology is pushing for really high volume work. And you do need excellent quality concrete to make that work. There's the material science and concrete and cement chemistry challenges in making 3D printing work, and essentially not having it look like toothpaste that's been squeezed out of the tube and sagged on your toothbrush. And yeah, you end up with something that looks like a pile of sausages unless you're very careful.
Yeah,
so
true.
So there is a lot of work going on, particularly through Europe and North America, and commercially in China as well, on driving these very high-performance mixtures for 3D printing. In terms of, let's say, achieving sustainability goals, I don't think 3D printing is heading towards sustainability in a way that other technologies can't. But as the materials themselves become intrinsically more sustainable, 3D printing will come along with that as a, let's say, as a premium technology would be how I would see it.
Yeah, awesome. That's awesome, John. So as we close it up now, what do you think will have the biggest impact on the buildings industry going forward in the future?
The need to reduce CO2 in every aspect of the material life cycle, and a deeper understanding of beyond CO2 impacts in these assessments. So we talk a lot about the CO2 footprint of the construction materials themselves, but there's a trade-off there against, well, not necessarily even against, trade-off back and forth with materials embodied CO2 versus a structure embodied CO2. And if we look at the structure in terms of how we put together a building, what we're designing a building for, let's say we put up an apartment complex in the inner city. These little shoebox apartments, they rent to students near universities, as a particular example I can see from out my window at the moment. The concretes in those will be specified with a 60-year, 80-year, 100-year service life. Realistically, do we expect that building to still be standing in 60, 80, 100 years?
Probably not.
If yes, excellent. But they should have designed it to look slightly nicer.
Yeah.
If not, then are we designing it in the right way? Are we designing our structures to make the best use of our materials? Then are we designing our structures to make the best use of our concrete? Are we designing our concrete to make the best use of our cement? Are we adding too much cement into our concrete to start with to gain these very long calculated service lives for structures that may not need them? So what we need is a very much more holistic view. And for me, as someone who works on alternative cements, people always come to me and say, oh, you work on these geopolymer cements. How much CO2 can you save by using this instead of Portland cement? And my honest answer is it depends. Because it depends which Portland cement product you're replacing, depends what's the application, depends what's the intended service life, depends what are the intended structural loads. It depends where you are, where you're transporting the materials from, what availability of raw materials you have, which aggregates you're using, how you're reinforcing it, a whole host of factors that you can't answer just by comparing cement A with cement B. So integration between materials research, structural engineering research, environmental engineering research, building physics. How does the air move within a building? How insulating is it? How can we heat it properly? All of these factors need to come together to do a proper sustainability assessment, not of a material, not of a component, but of a structure, of a system. And so the field has to move much more towards an interdisciplinary collaborative systems focus. And then going to supply chains as well.
Yeah.
As a material scientist, I may be talking myself out of a job here, but I actually see that as talking myself into a really interesting set of collaborative questions.
Yep.
Because they're things that materials is the underpinning technology of how all of this works, but we can't really make sense of a material in isolation without the context in which it operates. And so I think the future is contextual, it is situation dependent, and to be able to understand anything, we have to understand each thing locally. So a phrase I would like to use is, the global situation is not the average of every local situation, it's the sum of every local situation.
Wow. I'm just letting my brain trying to process that a little bit, but I love it.
So what that means is that by doing things, if you look at the global average of things, you can get nice graphs. You can get pictures that say, oh, we should all be doing the same thing.
Yep.
On average, every human being has slightly less than 2 legs. The average is not the right measure to use.
Gotcha. Awesome.
What we need is each local problem to be solved in the most appropriate way. The sum of those local problems is our global situation.
Yeah, nice.
Because every single case has mitigating circumstances, has special scenarios, has unique characteristics that are completely lost if you average everything. Right? If I take a hamburger as one of my favorite meals and one that I eat a lot, it's almost a balanced diet. You've got carbohydrate, you've got protein, you've got vegetables. If you were to eat a hamburger for every meal, every day, your body would probably get a lot of the nutrition it needed, on average. In a specific case, would you want to?
In one case, yes.
In one case, yes. Every meal?
No.
You don't always need the same solution to every problem.
Yeah. Yeah.
And a hamburger is a good average solution.
Love it. Just like you were saying earlier with Cuba having, the right materials to be using clay, and then other countries might be fly ash and so forth.
Even comparing the UK to Australia, similar levels of economic development. The UK has almost no fly ash. Australia's got loads.
Awesome. Cool. All right. Well, thanks so much for your time, John. That was absolutely phenomenal. And if people want to find out more about your awesome research you're up to, where can they find you?
We have a Twitter account, Cement@Chef. So Cement, ATSHEF.
Yep.
We have a group website where if you Google for Cements at Sheffield, you'll find our group website. Loads of publications, or if people want to send me an email, my email address is available, and I'm always happy to discuss on email as questions come up. I'm on ResearchGate if you want to request copies of papers through that. The usual places.
Hey guys, Adam here. Just before you go, just one quick request. If you're enjoying the show, please leave a review. It helps our rating and ranking on iTunes, so more people can hear from the people who are making our cities better places for our future.